Good morning, friends and colleagues representing various organizations, maybe some in the government, some in the private sector. I'm Dipinder Kapoor from NIUA, National Institute of Urban Affairs, making this presentation for the training program of ICAP. This presentation or this training, online training, is about sanitation and wastewater treatment technologies. So it is a technical presentation, and I will try my best in the time I have to share with you some of the critical elements and components of wastewater treatment systems, especially DWATs. So without further ado, let me put on my presentation, and I hope you will find it useful. So yes, so from here we begin. As I said, I am from NIUA, and the logos which you see on the top are on the left of the National Institute of Urban Affairs, which is a think tank working with the Ministry of Housing and Urban Affairs. It is based in Delhi. I represent the sanitation capacity building platform, the logo which you see in the center, as well as the National Fecal Sludge and Septage Management Alliance, the logo which is in the middle of NIUA and SUBP. EcoSan Services Foundation has been a technical partner with us in the sanitation capacity building platform to develop these training modules, and they are duly recognized for the excellent work which they have done in preparation in helping us prepare some of the modules. I have just two slides about what sanitation capacity building platform is. So the platform is a platform for a capacity building initiative on decentralized and on-site sanitation solutions. The platform has worked with various organizations, expert agencies to develop content, training modules, and is anchoring a national initiative for, broadly, it is called septage management. As part of a capacity building initiative, we also work on the policy and institutional development. So it is not just trainings. We also engage extensively in supporting institutions, whether they are para-state agency, urban local bodies, or national and state governments, and also on the policy inputs on decentralized sanitation and non-sewage sanitation solutions. The program is supported by Gates Foundation and has been going on from 2015. So this is a broad trajectory. This is the second slide of the platform of the work which we have done. So we started in 2016 by developing the platform, doing a capacity needs assessment, and doing a state engagement in UP. In 2017, we focused a lot of our efforts on developing content and training modules and partnering with the national mission institutions, training institutes like the Amrut Mission Training Institutes. We also started working in Rajasthan. In 2018, based on the work which we had done on the trainings, on the technical assistance, on the research, we came up with a state capacity building normative framework. So this normative framework actually tells any organizational agency how to do capacity building, what are the steps to be followed, and also lists down a set of 2 training modules, which we felt were very appropriate and useful for any organization to do capacity building. And this can actually be replicated in other sectors as well, not just sanitation. In 2019, in 2018, we also had our first engagement initiated with Uttarakhand government and also with the academia and universities to upscale capacity building. In 2019, we worked towards the second phase of the sanitation capacity building platform in trying to identify the niche and the priorities and developing more ensuring quality control and quality assurance of the training modules. And in the coming 2 years, we will be focusing on establishing a Center for Water and Sanitation at NIUA, and also as act as a knowledge hub and work with the government to promote decentralized sanitation. Now let's begin the presentation of this training module. Let's begin by water, because we are talking of water and wastewater. So water is important for us to see. A lot of information on this slide. Perhaps you may know of the water crisis and the kind of situation India is in. And we all know that water supply is defined by those three norms, those three dots which are presented in the center. A 40 liters per capita per day as a basic services standard for water supply in rural areas. 135 LPCD water supply as a basic standard for bigger towns and cities, and a basic minimum of 65 LPCD for other urban areas. What this water supply has resulted in is a generation of a lot of wastewater, which needs to be treated. So where does it come from? So the box on the left says 67% of our urban households don't have sewerage systems. It is online sanitation systems, septic tanks or holding tanks or pit latrines. And that is what generates about 80% of the pollution in our water bodies. If you look at the sanitation in urban India, we can look at it in terms of toilets, because Swachh Bharat mission focused essentially on toilets. We can look at the type of sanitation facilities, and then we can look at treatment. So the bar chart actually shows you that while the availability of toilets is very high, and we reached 100% open defecation target last year, the types of sanitation facilities is very varied and remains predominantly septic tanks, pit latrines, and others. What this has resulted in is that the treatment has been, it's not just the type of system there, but even the treatment of wastewater shows that only 62.5% of the wastewater generated is partially treated. And the STPs, which are sewage treatment plants, are only capable of, at the moment, treating 37.5% of the wastewater generated. And these are figures from the CPCB report of 2015-16. There have been significant achievements in sanitation, no doubt, under Swachh Bharat mission. And perhaps you may be aware of the numbers, but in terms of trajectory of achievements, we have reached ODF. We want to be ODF plus, and sooner we want to be ODF plus plus. So this is where the desired trajectory and the next steps are. So now let's come to the learning objectives of this session, training session. The learning objectives given to me for providing this session was to understand DWATs. What I have done is I have not only focused on the secondary treatment technologies, but also given a case study of a citywide decentralized sanitation solution system from the work which SCBP and IUA has done in Port Blair Town. So there's a case study, and there is the presentation and sessions on different technologies. So let's begin with this issue of water cycle and nutrient cycle. These two cycles have been there and in the nature, and they have not interacted, they have worked as separate systems over the past many centuries, millennia. So the water cycle starts with the water from oceans and land getting evaporated and coming down as rain, then going down as surface water, and then getting into groundwater and through the rivers into oceans. So that circle is on the left. Similarly, the nutrient cycle is all about the organic life. It's evolution, decomposition, recycling. So the food or any organic load gets consumed, gets digested or dies. It adds to the organic load on the ground through soil fertilization, goes through the plants and other microorganisms and comes back in terms of the food chain or the biomass. So these are the two cycles which have been going on. But what has happened in the last century or so with the increase of human population, both these cycles have got merged or have got mixed up. So what has happened is that digestion is happening, but it is being mixed with the groundwater or the surface water. So it's directly going untreated or undigested fecal sludge or human waste or other food waste directly goes and contaminates the water cycle and doesn't enter the nutrient cycle. So it leaves the nutrient cycle also diminished and it also affects the water cycle. So on the nutrient cycle, we have to add external fertilizers, and on the water cycle, we have to install treatment systems. Now let's look at a city and the different systems which actually we should explore, not just centralized system. So typically a city map is overlaid in the center of the city. There is a centralized system. NIUA being a hub of urban planners and architects and engineers, we know that the urban cities in the times of, say, partition for 1947 had a central core area which had a sewerage system. Then there was an old city which did not have anything, was more like a slum-like condition. And then we had planned colonies and cantonment boards, which were also planned areas with sewerage systems. But as the city expanded from this very central network system, and not all cities in India, more than 4,000 cities, only 400 cities have sewerage systems, and that too partial. But as the cities evolved, the central sewerage system did not evolve. Instead, we had various other types of sewage systems or just a drainage system in other parts of the peri-urban parts of the city. And this usually was just draining out into some stream. And later on, so what are the options therefore now are being presented? So you can have these shallow sewers which connect with your STPs, like those three dots would have been the STPs earlier on. So instead of opening it in the open areas, you can have shallow sewers. You can have DWAT systems also installed for these peri-urban areas. You can have electromechanical package treatment systems if DWATS is not feasible. In the peri-urban areas where agriculture is still there, you can have agriculture systems. Then there is this issue of public toilets and institutions. A lot of our cities have universities, colleges, and institutions. So for institutions, again, you can have DWATS, which is an institutional system, or you can have an electromechanical package system, or you or for these septic tanks and toilets which abound in different parts of the city. So it's just like a map of your towns and cities, the way it expands and how the urban sanitation systems cope up with it. So this is essentially the typology of different sanitation systems which you see. Now let's look at the septage and sewage, and its characterization is important. Septage is what is generated from septic tanks in the houses or institutions, and sewage is what is generated via flush systems through our sewerage systems and goes to sewage treatment plants. So how is septage different from sewage? There are different classifications or categorizations of characteristics which you can see on the left. But let's see which is the main one. So normally our treatment systems are designed on the BOD, biochemical oxygen demand characteristic. And the BOD can range in septage from 400 to 78,000, depending on the concentration of the septage. The standards for disposal or treatment are on the right side. So the standards are defined by the Central Pollution Control Board as well as the NGT. So while the NGT standards or the orders are very stringent, they ask for a less than 10 BOD for BOD, 10 milligram per liter standard for BOD. The CPCB standards, which are essentially followed by most cities, are more liberal. So this just to show that the standards are different by two organizations, Ministry of Environment and Forest and Climate Change, whereas NGT orders are more stringent. But yes, the cities follow MOEFCC orders, not the NGT orders. Let's look at the type of containment systems. Since this training session is more on treatment, I will not delve much on the containment systems. Suffice to say that the containment systems, at least some of them, are also primary treatment systems. So like a twin pit toilet, which you see in the center, where one pit fills in and the other will fill in. So in 6 months' time, the fecal waste does get decomposed and treated and can be used for agriculture. But if it's a single pit or if it's an improperly designed septic tank, then there is no treatment happening. So for a treatment for a septic tank to have proper treatment, it has to have a structure, and also for a biodigester has to be properly designed. Then only it becomes a partial treatment system. So when we talk of secondary treatment systems, let's categorize the typologies of the treatment system. One can be mechanized and one can be a non-mechanized treatment system. DWATS, the focus today is more on the non-mechanized systems, whereas the mechanized systems are usually followed in either sewage treatment plants, which deal in large volumes, or in the packaged small decentralized treatment systems. So what is the selection criteria by which you decide? That is important. When we do wastewater treatment, it is done with 4 meta objectives. One is we need to separate solid waste from water, and not just separate, but to discharge or reuse them as per standards. So that's the first principle of wastewater treatment, how to separate solid from water. Then, then comes the treatment objectives. To what end you want this treatment to happen. So if bio-oxidizing the solid and removing the contamination is an objective, but to what extent do you need to treat it? Because if you want to use your treated water for agriculture, you may not require a very high treatment for removing nitrogen and phosphorus. That still serves the agriculture use. Then comes this issue of suspended and non-settlable colloidal solids. So these, of course, are something which is a part of your solid waste and water separation. And this can be used, treated in different formats, which we will see. And of course, you want to remove specific trace organic constituents and elements. That again depends upon your objective for treatment. Broadly, the typologies of secondary treatment are aerobic, anoxic, anaerobic, combined, and lagoon process. These are all broadly falling under biological treatment processes, which we will be discussing in detail. We will not be discussing the mechanical ones here because that requires another session, and that is something which is not related with DWATs. Each of these elements will be explained to you in the following presentation slides. So most of the aerobic processes, let's start with the aerobic processes. They provide a carbonaceous by BOD removal and nitrification. So it's important to remember what the aerobic process does. What the anoxic process is is like the anaerobic process. It essentially does denitrification. Most of the anaerobic processes do carbonaceous BOD removal, as was said, also nitrification, and they also stabilize because uh, you ensure that the wastewater comes and is stabilized for removal of these contaminants. And then we have the combined processes, which is a combination of aerobic and aerobic. So since it's a combination, it does everything. It does BOD removal, it does nitrification and denitrification, and also phosphorus removal. So therefore, the combined process is like the gold standard or epitome of DWATS. And you will see the DWATS process is like a combined process, which will be explained soon. So let's look at the non-mechanized biological and non-biological treatment systems first. One of the first treatment systems is an anaerobic baffle reactor, which in a way simulates the septic tank, but it has a series of tanks. So it is called anaerobic suspended growth biological process. Why it is called this? It is called this because the fecal sludge is suspended and biological growth happens without uh, any kind of triggering or movement. It happens in suspended solid. So this is a typical anaerobic baffle reactor, which does treatment for BOD and TSS and has a hydrological retention time or the water retention time of 1 to 3 days. It does require 1 to 3 days to do treatment for BOD up to 70 to 9% and for TSS from 80 to 90%. Next is the anaerobic attached growth biological process. So this is again anaerobic, like the previous slide. The only difference here is you have medium or you have filter medium attached in it. Sorry, there was an interruption. So in this, what happens in the anaerobic filter, attached filter is the attached medium provides the microbes a home to settle, and therefore the treatment, the BOD and the TSS removal is higher as compared to a non-medium one. Then we come to the constructed wetlands. In constructed wetlands, we have a system where what is also called attached growth hybrid biological process, because in this we provide uh, uh, a plants on and rhizome network on which this attachment can happen. Microbiological attachment is possible. So we have now come to the attached growth, and it's hybrid because it is both. Um, it happens both anaerobic and aerobic. So now is this example of a DWAT system. What a DWAT system is a patented name to explain a combination of technologies and treatment systems which tries to treat both the solid as well as the wastewater. Um, so typically it has a grease trap, then there is settler, which tries to remove, which removes the, settles the solids and treats it separately, either through a biodigester process where the solid generates methane gas, which can be extracted, and then the liquid is made to flow into the ABR and the anaerobic filters and the blunted gravel filters, finally either to a polishing tank or a soak pit. So this entire process is called DWATS. What is important to remember is that this is a treatment system which has a relatively low treatment capacity, maximum 500 KLD. After beyond that, it is difficult to sequentially pass a large volume of wastewater in this process. And you can also remove the biogas digester because that requires time, and then it can be fastened and depending upon the characterization of fecal sludge available. It is usually popular because it works without energy, although it cannot be switched off. Continuous operation without much of an additional external input. However, it is not the best solution everywhere, and it is suitable where skilled and responsible operations is possible. If the operators are not there, and if it is, so if the solids are not taken out and if the filters are not cleaned, it can lead to a disruption. Next slide is the waste stabilization pond. The waste stabilization pond imitates a lagoon biological process which happens in the nature. But it is simulated here to become a hybrid system. So in the first lagoon, there is an anaerobic treatment where the sludge settles below and is undergoes anaerobic because it doesn't get into touch in contact with the air. And in the second tank is a little shallow. So it's a facultative process where both aerobic and anaerobic happen. And finally, the third lagoon, the water flows from one to the second to the third, is an aerobic maturation stage where entirely it's a very shallow and oxidization happens. So this is also a process which is feasible for treating larger volumes of water and gives a very high treatment of BOD and TSS, although the retention time is also longer in this case. Now we are speaking of combined hybrid biological processes. Why we are speaking of combined hybrid and biological is because we are adding algae or any other medium. So it is combined because it is anaerobic and aerobic, and it is also biological. So for that reason, you have covered anaerobic ponds, and then you pass the treated sludge from there to an algal pond, and then you have, like the lagoon, you have maturation ponds and the rock filter. So it's not, I don't think this has been tried in India as yet. It requires a good process where you ensure that the high rate algal pond actually circulates the algae and the sludge over a period of time, and that is why it's a little complicated. Soil biotechnology has been promoted in India by IIT Mumbai and is being tried in different areas. It simulates the it's a biological process which simulates the planted wetlands. So you have plantation, you have filter medium, and you also treat the wastewater which comes out from here uh, into a process. So it's a combined hybrid process, and it is usually it's actually quite extensively done in some of the fecal sludge treatment plants in India. Now let's discuss the mechanized treatment systems. So the mechanized treatment systems are activated sludge process in which the BOD removal happens. Um, and sorry. So the activated sludge process is called an aerobic suspended growth biological process precisely because the suspended, there is no turbulation in this. So the tanks are not, uh, the wastewater is meant to, is not, uh, sorry. So there is just air which is made to flow in a suspended sludge tank, and the aeration leads to digestion and oxidization of the microbes. And then in the next tank, the clarified treated wastewater is there, and again desludged is desludging at the bottom happens, and that part of that sludge is brought back again into the first tank where compressed air is put in, and in this process the treatment happens. The upflow aerobic sequential batch reactor UASBR is also an anaerobic suspended growth one. The only difference is that unlike the previous one, here the inlet of the sludge is from below, and it is through pressure it is made to go up, through the sludge is made to go up, and in the digestion which happens in this process, the gases which are released are collected in terms of a tank. So that is the only difference that it captures, and therefore it has a retention time, because to generate gas you need to retain it. So the minimum 2 hours is required, and it can be even longer depending upon the size of the tank. A sequential batch reactor, as the word says, is a reactor which is in sequence. So this is done by ensuring that there is more than one batch of treatment happening. So you may have 2 or 3 parallel systems where one batch or the one unit is shut down and the second unit is operating, and then the second is shut down or the third one is operating, depending upon the inflow of the sludge. So the process is the same. You do aeration first, then you do settlement, and then and decant the treated water and excess sludge. So, but you do it in sequence in different batches, and that is in this way you are able to treat. You're able to do a high volume of treatment. Now we come to this attached growth biological process called the moving bed biofilm reactor. The only difference here is these components which are added. These are MBBR media. This media is of different types, and depending upon the surface area, it can be plastic things, or it can be very soft tissues like this which are added, and the surface area of this medium generates the place where the microbes can stick and larger digestion can happen in the treatment process. Then we have the last one is this membrane bioreactor. The membrane bioreactor is essentially this membrane in the middle, which is provided for the bioreactor to, the rest of the processes are fine. It comes in through an anaerobic process and then goes to an aerobic process. And there you also add a membrane. So this provides a very high level of treatment. The membrane is like our um, RO membranes of different intensity and depth, density, and they treat the water to desired standards. So let's see the technology comparison of all the technologies presented. So there we will see that the there are different characteristics we have kept here is for land area, energy required, capex, opex, and all these technologies give you different results. So for example, the DWATS land area required is high, capex is high, but opex is low. Whereas for a membrane bioreactor, the land area is very less, 1 meter square for 1 KLD of wastewater treatment. But at the same time, the capex is high and the opex is moderate. and you also have an energy requirement. So these are some of the characteristics which can define the choice. If you don't have land, then DWATs and wastewater stabilization tanks will not be very useful. I've added some slides of current uh, uh, examples of constructed wetlands, which is being was tried many years back in Indian Agriculture Research Institute in Delhi. And you will see it was designed for a 2 MLD treatment, which is quite high, and the area was 1.42 square meters. The cost was less because it was at least 2 decades before. So this is the kind of constructed wetlands which was created in IARI. Then let's look at the other one, the Arvind Eye Hospital, which did a DWAT system, and you will see the design capacity was only 320 KLD compared to 1 MLD or 2 MLD previously. And this was also done in a very scientific manner, and it is working very well. This Arvind Eye Hospital in Pondicherry. Then we have the ABR, and a very good and old example is in Bhuj, in Bankers Colony in Gujarat, a very small treatment system for one colony of about 30 KLD. Area required was also less, 300 square meter, and at that time, this is also about 15 years old, 20 years ago, so the cost was also quite low. So this is the well-designed and very artistically designed treatment system in Bhuj. Last is these waste stabilization ponds. The example I could come up with was the Mathura one, where they did all those three stages of tanks, 1 and 2 for anaerobic, 3 to 6 for facultative, and 7 to 8 for maturation. So different cities, some experiments and attempts have been made. Okay, the SPT also was there. This was the IIT Mumbai one. It was designed for 3 MLD and it cost about 3 crore. The only thing is you have to add medium to it. So this is the SPT technology at Worli, Mumbai. The MBBR reactor is, you can see this from an STP example. So a sewage treatment plant, you will have this medium which is there. You can see that black one. So those are those plastic mediums on which the microbes are settling. The membrane bioreactor is like this, and it has been done in Ahmedabad and several other cities. The water is actually made to pass through this membrane. And there is also flushing and cleaning of the membranes. So there are two tubes. One is for the water treatment. The other is for flushing of the films which get jammed. Now, this is a presentation on the Port Blair city of decentralized sanitation solutions which we did. And this is an example of how a combination of centralized and decentralized systems can actually work. I don't need to explain this. On the map on the right, that big line which you see in the center is the airport, is the landing strip of the airport. It's a small island, and a population density is quite high given its location. At NIUA, when we went there, we were shown a DPR which was prepared by WAPCOS about 7 years ago. It had suggested a treatment system which costed about 152 crores for sewerage and 15 crores for lift pumping, and had a very high OPEX of 62 crores about 7 years back. So we were asked to review the DPR and suggest if some decentralized treatment systems can be applied. So we did a visit and we did a review of the DPR, and we came up with our findings. So what we saw was that in the map, there are two areas where there was one catchment area which we called STP-A and one for STP-B, which we felt was okay because these were in high density areas of the town. and they did not have adequate land for any other treatment systems. So we were okay with these two plants which were suggested, and each one was a 10 mld and the other was 1.2 mld. Now we were looking at the phase 2 of this 15 mld. So we were trying to explore what can be the option. Now the DPR of the revised DPR of WAPCOS said that if you do it like this, if you have these 3 treatment plants, then the capex is this much and the opex is this much. So, but the project cost had inflated and it was now close to 324 crores. So we did an estimate of, we did an analysis of what they had presented to us, and we came to this conclusion that pumping station and the STP costs was very high. And what we therefore proposed was shifting from gravity sewers to solid free sewers in some area, design the STPs to include co-treatment of fecal sludge, and also setting up of a fecal sludge treatment plant. So we had this kind of a three-tier approach. We accepted that some areas would require centralized systems, but some can actually work in combination with a solid waste sewers and an FSTP, and then therefore more STPs can also be, more decentralized STPs can also reduce the OPEX cost and design and increase the life of the fecal sludge treatment plant. So the design approach we had therefore was, instead of 3, now we had 7, so 6. So the zone A and B were 2 decentralized STPs, and we suggested these 4 more, 1, 2, 3, 4 more decentralized sewage treatment plants of smaller capacity. Essentially, this would reduce the pumping cost, and that was the major consideration for suggesting more of decentralized systems. So when we did a review, we found that a centralized approach of a sewerage system is expensive. It would be about 206 crores would be the capex, whereas the decentralized would be much less, and the opex would be significantly less. Nearly half of the opex of a centralized system would come from a decentralized approach. And this decentralized approach, I'm not saying DWATs alone, it's also decentralized STPs of smaller capacity. Their pumping and their transference cost will be much less, because we know in Port Blair, the cost of 1 unit of electricity last year in 2019 was 28 rupees per unit, because they do it based on diesel. So the recommendations which we gave from NIUA was a combination of decentralized wastewater sewage solutions. We said a non-sewage seaward fecal sludge treatment plant should be there. And for the 25 mld of wastewater, at least 6 decentralized STPs are required. We also provided action steps, what needs to be done fast and what can take. And we also provided some other important priorities which the water board there needs to take up. So the last part of my presentation here is on water reuse. So the water reuse is what is water reuse and what is its unique selling proposition, or the USP? Actually, we are talking of water reuse because we are in a water crisis situation where our cities are supposed to run out of water soon. So in simple terms, water reuse is the recycling of wastewater, treated wastewater, for a wide range of beneficial purposes. And its treatment is based on the objectives or outcomes which you want to achieve. So if you want if you want to use the treated wastewater for agriculture, irrigation, if you want to use it for minimal gardening or for industrial use, or for direct potable or high quality processes like drinking water, bathing, and industrial processes, There is a flow of treatment cost which is moves from low to high, and also the recovery, cost recovery of treated wastewater is like this. So, for example, for agriculture, you just need a secondary treatment to get the BOD levels which are appropriate, and then that can be used for agriculture and irrigation. Otherwise, for other purposes, you'll have to do more treatment. You'll have to do a secondary treatment. You'll have to do membrane filtration. You'll have to remove the nutrient, nitrogen and phosphorus. So, or you'll have to do RO and disinfection. So that those are the costs and those are the treatment options which are there. So it all depends on what you want to reuse the water. So I do know Bangalore is reusing its treated wastewater from STPs for agriculture now. So in which case you don't need to remove nitrogen and phosphorus from this, because that is actually an input for agriculture. So that defines your treatment framework. So different sectors can use it. Agriculture sector can use, urban local bodies can use, and the industrial sector can use. Thank you. For more information on the decentralized and on-site sanitation systems, please do visit our website, scbp.niua.org. Thank you.